The USS Frank Knox strikes the unyielding coral of Pratas Reef at a speed of 16 knots. The kinetic energy of the impact drives the destroyer hard onto the submerged structure, violently halting thousands of tons of steel. This is no glancing blow. The ship plows directly onto the reef in the South China Sea, grinding forward until the friction of the coral overwhelms the mechanical momentum of her steam turbines. Deep inside the forward section, the collision registers as a catastrophic deceleration. The immediate threat is not just flooded lower compartments or stranded personnel. The true crisis lies higher up in the forward superstructure. The Frank Knox is a radar picket destroyer carrying a sensitive combat information center and a high-value electronic suite. Hardware assessed at well over $15 million. If the ship goes down, this state-of-the-art Cold War technology is lost or left vulnerable to hostile recovery. The grounding occurs on 18 July 1965. The vessel is operating in a highly sensitive maritime theater where navigational margins are unforgiving. Pratas Reef is an isolated geographical feature, rising sharply from deep water to create a submerged hazard of hard, jagged coral. When a massive steel warship hits a rigid obstacle like this at operational speed, the structural damage is profound. The forward hull absorbs the absolute brunt of the collision. Steel bottom plating is torn and scoured as it grinds against hard coral. Seawater begins flooding the lowest forward spaces first, and the loss of buoyancy starts to drag the bow down onto the reef. In the critical moments that follow, the crew initiates standard naval damage control protocols. The propulsion systems are secured to prevent further mechanical self-destruction. The immediate tactical focus shifts entirely to containment and dimensional assessment. Soundings are quickly taken over the side to determine the exact geometry of the stranding. The resulting data confirms a massive operational failure. The destroyer is firmly and deeply pinned onto the reef. As seawater floods the lower decks, the ship takes on a sustained about 6-degree starboard list, settling unevenly on the jagged coral shelf. The warship is bleeding oil and water, permanently locked in a static position against a highly dynamic ocean environment. The officers on the bridge face a stark reality. The ocean does not stop moving, but the Frank Knox is completely immobile. The stakes of this stranding extend beyond the physical loss of a single hull. The geopolitical environment demands absolute operational security for advanced fleet radar systems. The electronic suite housed in the forward section is a multi-million-dollar investment. And far more than money, it is designed to track distant airborne threats, coordinate regional fleet defense, and manage complex combat information. Leaving it intact on a stranded vessel out here is an unacceptable strategic risk. Scuttling the ship with explosives to protect the hardware is a terminal last resort, one that Naval Command is not prepared to execute without exhausting every salvage option first. The central objective is absolute recovery. The ship and her classified payload must be forcefully extracted from the reef. However, the physical reality of the grounding presents an immediate blockade to that recovery objective. A warship is designed to float evenly in deep water, where the ocean provides uniform support across the entire length of the hull. On Pratas Reef, the Frank Knox is suspended awkwardly across rigid, uneven points of hard coral. The bow is heavily grounded and taking on dead weight from flooded seawater, while other sections of the ship remain unsupported. That persistent starboard list is the clearest indicator of how badly the weight is distributed. Every passing wave and tidal shift applies unnatural kinetic force to a steel structure already compromised by the violent tearing of her lower hull plates. The immediate wartime salvage imperative is clear. The Navy must rapidly mobilize a dedicated fleet to pull the stranded destroyer off the coral before the marine environment degrades the physical situation further. Time is the absolute first antagonist. The longer the ship remains pinned to the reef, the more vulnerable she becomes to the relentless forces of the sea. The salvage engineers arriving on the scene will not be fighting enemy combatants. They will be fighting the cold geometry of the reef and the inert dead weight of the stranded vessel. The Frank Knox is stranded in hostile waters, but the true danger is not enemy action. It is the ocean itself, preparing to tear the ship apart. The exact geometry of the stranding creates a lethal mechanical trap for the salvage operation. A mix of salvage ships and tugs races to the coordinates, anchoring around the stranded warship as the response builds over the next hours and days. They arrive prepared for a standard rapid extraction, carrying heavy wire rope and massive mechanical winches. Their objective is to attach tow lines, build up tension, and rip the destroyer off the reef and back into deep water. However, the physical reality of the seabed immediately dictates otherwise. The coral is not a smooth ramp. It is hard coral heads and ridges, uneven and unforgiving, that bite into the torn bottom plating and hold the ship fast. The primary enemy for the salvage engineers is the physical principle of ground reaction. This is the dead weight friction that occurs when a vessel loses its natural buoyancy and transfers its mass directly onto the seafloor. When a ship is floating, the ocean supports its entire weight. When it runs aground, every flooded compartment and every inch of hull pushed up out of the water represents thousands of tons of downward force pressing into the reef. The warship is no longer a floating vessel. It has become a massive steel anchor bolted to the earth by gravity. The ground reaction is so immense that any pulling force must first overcome the crushing friction of the hull pressed down onto hard coral. Loads measured in hundreds of tons, not wishful thinking. Complicating this massive deadweight friction is a severe structural spine threat, formerly known as hull girder stress. A naval destroyer is essentially a long, hollow steel beam. On the reef, the sea's even support disappears and the hull is left hanging on a few brutal contact points. Gravity pulls down on the heavy, unsupported ends of the ship, while the unyielding seabed pushes upward against the pivot points. This creates immense bending moments along the continuous longitudinal structure of the ship. The stranded destroyer is trapped in exactly this type of critical bending moment. The forward engineering spaces are flooded with heavy seawater, pulling the bow downward, while the midsection is rigidly pinned over a coral peak. If the 5 towing vessels attach their heavy steel cables to the stern and apply maximum pulling power, the ship will not slide gracefully backward. The ground reaction locking the bow is far too high. Instead, the pulling force will concentrate entirely at the point where the hull rests on the reef. The violent tension will exceed the tensile strength of the steel framing. Applying brute mechanical force will simply snap the hull girder in two, just tearing the ship apart and sinking the forward section along with its invaluable payload. Despite these severe mechanical warnings, standard procedure dictates that conventional salvage methods must be attempted first. The diving teams enter the water to assess the damage and patch the torn lower plates wherever they can reach them. Giant salvage pumps are hauled aboard the listing deck to forcefully expel the invading seawater and restore internal lift. The fleet tugs lay out thousands of feet of heavy cable and massive anchors, a specialized rigging configuration known as beach gear, designed to multiply pulling leverage. The winches are engaged and the towing vessels throttle up their massive diesel engines to apply steady, grinding tension to the stern of the warship. The conventional attempts fail completely. The massive ground reaction holds the bow firmly in place. The pumps cannot overcome the rapid influx of seawater rushing through the torn bottom, meaning the dead weight friction remains absolute. As the tow lines draw tighter, bending loads spike toward catastrophic limits, and the towing masters have to back off before the hull tears itself apart. The fleet is stalled. The reef's static grip makes brute pulling not just useless but lethal. The salvage engineers are out of conventional options. They must find a completely different mechanical approach. They must figure out a way to break the reef's grip before it breaks the ship. Trading the structural survival of a warship for a path back to deep water requires a brutal calculation. Salvage leaders turn to explosives, not to gouge a grand new canal, but to break off the coral points that have impaled the hull. The aim is selective clearing, reduce the hard contact points, ease the grip of the reef, and give the pulling gear a fighting chance. Explosive trenching in a shallow marine environment is a highly volatile operation. Divers must descend into the turbulent surf zone immediately surrounding the grounded ship to manually position the demolition materials. They are forced to work in treacherous, surging water, placing the explosive charges close enough to the seabed to pulverize the solid rock. At the same time, they must somehow direct the immense explosive energy away from the extremely thin steel bottom of the destroyer. This is an almost impossible balancing act, because water transmits shock far more efficiently than air, and a submerged detonation can drive punishing pressure waves into steel in ways an open-air blast cannot. The margin for error is virtually non-existent. When the firing circuits are finally closed, Massive geysers of white water, pulverized rock, and fractured coral erupt violently around the stranded vessel. The desperate strategy backfires in the worst possible way. One major blast does not open a clean escape path. It hammers the underside of the grounded ship, enlarging damage and opening fresh flooding routes. It also tears out some of the provisional buoyancy work the teams fought to build. Yet the use of explosives does not end here. The lesson is brutal and immediate. From this point on, blasting has to be selective, controlled, and focused on removing impalements rather than chasing a mythical trench. As the physical integrity of the hull deteriorates, the environmental situation escalates into a catastrophic, unrelenting threat. The South China Sea in summer can spawn repeated cyclonic systems, and the salvage site is threatened again and again for weeks. Typhoons and tropical storms drive heavy seas across the reef. A fully operational warship can meet that punishment bow on. The immobile destroyer cannot. Pinned on the reef, she is forced to absorb the ocean's energy, broadside, wave after wave. When the first typhoon approaches, salvage operations are forced into survival mode. Many ships have to sortie to deep water to avoid becoming casualties themselves, and the work pauses or shrinks to whatever the weather allows. Lines are eased, anchors recovered, and the station is thinned to the minimum that can be held. The stranded vessel takes the brunt of the storm. Waves lift and drop her against coral, driving her deeper, opening new leaks, and compounding the load with every violent cycle. By the time the third typhoon finally passes and the salvage tugs are able to return to their pulling stations, the operational picture is incredibly grim. The coral reef remains entirely unbroken, while the lower hull is severely compromised by both the initial grounding and the subsequent explosive shockwaves. The weather windows are entirely unpredictable, and the massive mechanical pulling gear remains useless against the deep friction. Violent weather and backfiring explosives have completely shut down all conventional options. The engineering team is backed into a dangerous corner, forcing them to orchestrate a completely experimental pivot to save the ship. The salvage engineers do not abandon pulling, they change what pulling can accomplish. Beach gear remains rigged, the tugs stay on station, but the operation pivots from brute force to changing the ship's internal physics first. If they cannot drag the destroyer out as she is, they must drive the water out of her broken spaces and claw back buoyancy before the next sustained pull. They deploy a highly experimental chemical buoyancy injection system directly into a combat zone. The method requires pumping a specialized two-part liquid urethane mixture deep into the flooded steel bowels of the warship. When these two dormant chemicals are combined under pressure, they trigger a violent exothermic reaction. The liquid rapidly expands into a dense, rigid polyurethane foam. As it expands, it forcefully displaces the invading seawater, filling every void, pipe, and torn bulkhead space. Unlike standard compressed air, which immediately escapes through jagged openings in the bottom plates, this rigid foam hardens in place. It creates a cast-in-place, buoyant structure that displaces water and helps the ship hold what buoyancy she can regain. It also adds internal support across battered boundaries. Not a perfect seal and not immune to heavy seas, but a powerful insurance factor that reduces flooding risk and eases the worst bending stresses long enough for pulling operations to continue. Slowly, compartment by compartment, the internal geometry of the warship transforms. The massive volume of heavy seawater is steadily replaced by thousands of cubic feet of lightweight, rigid foam. The incredible weight pressing down onto the jagged coral begins to decrease. The ship regains thousands of tons of artificial buoyancy. The bow, previously anchored to the seabed by the weight of the ocean, begins to exhibit positive lift. The previously vulnerable hull, formerly on the verge of snapping in two under the severe bending forces, is now rigidly supported from within by the dense chemical structure. The internal bleeding of the warship is finally stopped and her structural integrity is artificially restored. The engineering pivot is a massive technical success, stabilizing the spine and restoring vital lift to the crippled destroyer. The vessel is no longer an inert piece of flooded steel bleeding on the rocks. However, this chemical resurrection only solves half of the mechanical equation. The ship is structurally sound and artificially buoyant, but the jagged coral shelf still tightly grips the lower hull. The massive static friction of the reef still holds the vessel captive against the pulling tugs, waiting for one final application of physical force to break the deadlock. The towing masters signal the fleet to advance their throttles, commanding maximum revolutions from their massive diesel engines. Heavy steel cables rise out of the sea, violently shedding seawater as they pull dead taut against the stern of the stranded destroyer. The heavy deck hardware groans under hundreds of tons of extreme mechanical tension. Despite the immense, sustained pulling force, the destroyer does not move. The jagged coral shelf refuses to surrender its grip on the battered lower hull. The salvage engineers face a brutal physics problem on the open ocean. The reef still has the hull in a hard lock. They realize they need a sudden, violent jolt, something that can lift and loosen the ship for a split second while the tugs are already at full strain. The solution requires generating a localized hydraulic shock to physically dislodge the immense steel structure. This specialized technique, known as artificial wave rocking, relies entirely on the immense kinetic energy of an external wake. The mechanical theory dictates that if a heavy wall of moving water lifts the stranded vessel by just a few crucial inches, the temporary upward surge will momentarily eliminate the bottom friction. In that exact fraction of a second, the ship will transition from a static, anchored object to a dynamic, floating mass. If the salvage tugs are pulling at their absolute maximum tension during that precise moment of upward lift, the vessel will instantly slide backward off the coral before gravity can slam her back down onto the unyielding rock. It is a highly dangerous, perfectly synchronized application of external hydraulic force and extreme mechanical tension. To execute this violent maneuver, the command brings in another destroyer, the USS Cogswell. Her captain receives orders to run at operational speed past the salvage site, holding a parallel course just outside the worst of the reef. As her bow drives water aside, the transit throws a heavy wake toward the stranded ship. A man-made surge meant to lift, rock, and momentarily loosen the reef's grip. The timing of the operation must be absolutely flawless. Out on the deep water, the salvage and towing fleet holds their heavy winches at the extreme breaking point. The thick steel tow lines tremble under the incredible strain, stretched to the absolute limit of their tensile strength. The engineering teams brace themselves on the listing deck of the stranded warship, watching the horizon as the towering wall of displaced water accelerates toward their exposed flank. The heavy wake strikes the stranded warship broadside, and the ship answers with movement, not a clean leap, but a hard incremental wrench. With each surge, steel grinds on coral, and the hull shifts inches at a time. Then, on a perfectly timed lift, the ship finally breaks the static lock. The beach gear and tugs take that fleeting moment and turn it into distance, hauling the destroyer aft in a single decisive slide off the reef. After an agonizing 38 days aground, the massive warship finally slides completely off the unyielding seabed and plunges backward into deep water. The savage combination of rigid internal chemical lift and dynamic exterior hydraulic force successfully overcomes the immense environmental trap. The vessel floats free, her torn steel bottom suspended safely above the deep ocean floor. The towing masters rapidly adjust their heavy rigging to secure the freshly liberated mass, verifying that the internal chemical cast is holding firm against the cold seawater. But surviving the immediate extraction is only the first step toward safety. The critical time window for survival does not close the exact moment the warship slides off the reef. In the immediate hours following her violent extraction on August 24, 1965, the crippled destroyer must prove she can survive the open ocean. The salvage and towing vessels rapidly transition from static pulling gear to a dynamic deep water towing configuration. The extreme mechanical tension required to drag the ship off the coral is replaced by the steady, rhythmic strain of a long-distance tow. Out on the deep water, the immense deadweight friction is finally gone. But a new physical threat emerges. The deeply fractured lower hull must now absorb the continuous hydrodynamic force of the open ocean without the solid support of the seabed beneath it. Inside the battered warship, the engineering teams carefully monitor the internal chemical cast. They must ensure that the massive volume of rigid foam holds its shape and maintains its absolute bond with the torn steel. If the extreme flexing of the hull under tow causes the chemical buoyancy to fracture or separate from the bulkheads, seawater will rapidly flood the carefully sealed lower spaces. The ship would quickly lose her artificial lift and founder in deep water. However, the intervention proves to be structurally sound. The hardened polyurethane material effortlessly absorbs the bending moments of the ocean swells, keeping the heavy forward section firmly afloat. The lethal physical trap of the reef has been completely defeated by applied chemistry and calculated hydraulic force. The primary strategic imperative of the entire operation is achieved, high above the waterline. The forward command and control spaces ride over the waves, and critical electronics are reported largely undamaged by the stranding itself, even as other equipment is offloaded to lighten the ship. The Navy avoids losing high-value systems to the sea, and it avoids the grim alternative of destroying them in place. The staggering logistical effort to deliver experimental materials into a typhoon-threatened zone pays off. The warship is carefully towed across the ocean to a safe harbor, where heavy dry dock facilities wait to permanently repair her mangled steel bottom. When the ship is finally lifted out of the water, the true extent of the violent grounding is fully revealed. The abrasive coral formations completely destroyed the lower plates, tearing massive holes through the outer skin of the vessel. Without the rigid internal chemical lift filling those shattered voids, the structural spine of the ship would have easily fractured during the long tow. The visual evidence confirms that the salvage team made the exact correct calculation when they abandoned brute force. Their decision to halt conventional operations and fundamentally alter the internal physics of the ship is the sole reason the vessel survives. The ultimate validation of this unprecedented operation is written in the subsequent history of the vessel. The Navy does not merely patch the damaged destroyer and send her to the scrapyard. The ship undergoes a comprehensive structural restoration and returns to active operational duty. She goes on to serve out her original lifespan and continues her maritime service for decades longer in foreign navies. A warship that was absolutely guaranteed to snap in half on a remote reef instead sails thousands of additional miles, all because an unnamed engineering team refused to blindly apply mechanical tension to a trapped hull. Heroism in extreme marine salvage is rarely found in reckless action. It is found in technical discipline. It is the ability to stand on a sinking, heavily listing deck in the middle of a cyclonic storm track and correctly diagnose an invisible mechanical failure. The salvage masters recognized the absolute limits of their heavy equipment and chose to stop pulling before they destroyed their own objective. They traded heavy explosives and massive towing winches for chemical ingenuity and dynamic hydraulic timing. By successfully forcing an immobile steel casualty off an unyielding coral shelf, they executed one of the most remarkable technical recoveries in modern naval engineering.